In this video, we're going to talk about confidence and prediction intervals for the response variable, given that we're starting with a particular value for x. So what we mean by that is, in addition to trying to make inferences about what the true slope or the true intercept is, we can also make estimates about what's going on at any particular x value. So if I kind of have y over here, if I have x over here, instead of trying to talk about just the slope or the intercept, I could also talk about I had this observed x value. This is the x value that matters. What do I know about the response when x equals this value, right? And so maybe I have some data, right? And so I can kind of, draw my regression line. I can predict, I can have my best guess for what y is going to be given this x value. But maybe I want to make a confidence interval for the mean response, the mean y value at this x value, because it's probably not going to be exactly what's on my regression equation, right? So I have my line of best fit, but I probably want to make kind of an interval around this, such that I'm confident that the true mean response for y is in that interval there. A prediction interval, we call it a prediction interval because we're not estimating a parameter. We're just estimating the y variable in general. So we're basically asking, if we make it, say, a 95% prediction interval, we're saying, what is the range that set 95% of the response values are in this range at a particular x value? So instead of just, I should really make this a lot wider to make a point. So I think that's probably enough. So I have something that looks like this. Then my prediction interval at any given x value is going to have to be wide enough to include about 95% of the possible values in y at that particular range, whereas a confidence interval for the mean response is going to be a lot narrower, right? So that's just trying to estimate where the mean is. A prediction interval is trying to estimate where 95% of the possible values are going to be. And so I forgot I actually have this nice picture from the book. Instead of me drawing crappy drawings, we could just look at this and kind of see the difference that the prediction interval is a lot wider. The confidence interval for the parameter is a lot smaller. And so one thing that helps us do this is just kind of this reminder that when we have our assumptions true for a linear relationship, then the distribution of y at any given x should be normally distributed. So that helps us both with prediction intervals and gives us kind of the undergirding for why we can do a confidence interval there as well. So let's start with the confidence interval for mean response. So our best guess for y, I should go back to this. Our best estimate for y is going to be our regression equation. So beta hat naught plus beta hat 1 times x is our best estimate for y. Well, the expected value for this is just going to be the true parameter, whatever that true relationship is. And the variance of y hat is going to be this expression right here. And so that helps us because we need to eventually get to a standard error for y hat, which is going to be just the square root of this version and with s sub e plugged in because, again, we're estimating it with our sample information. We don't actually have the true parameter for that measure of variability. So that means that we can calculate a confidence interval for y hat by starting with our y hat value as our point estimate, plus or minus the appropriate t-value times the standard error for our y hat estimate. So as an example, let's again work with our stopping distance question, this time with the purpose of doing a confidence interval for the mean response when the speed of the car is 20 miles per hour. So we're trying to estimate the true mean stopping distance for a car given that the car is moving 20 miles per hour when the brakes are initiated. So we know what our best estimate for that stopping distance is based on our regression equation. We can also calculate the standard error for y hat, so how much error we should generally expect to see in y hat from sample to sample. We have 50 observations. This is the appropriate t-value for degrees of freedom is 48 and 95% confidence. And again, we could do, I keep doing 95% confidence. We could do any confidence level we want. 95 is obviously a very typical one, but we could certainly adjust that t-value depending on if we wanted to say 99% confidence as well. Okay, so my best guess, I need to calculate y hat first because that's not fully calculated here. So I'm going to plug in 20 for x and then calculate this value. So it's going to be negative 17.5791 plus 3.9324 times 20, and I get 61.0689. So then my interval is going to be y hat plus or minus t times standard error of y hat. So then that's going to be 61.0689 plus or minus 2.010635 times this 2.895501 value. And so if I start with the lower bound, I'm going to do minus 2.01, minus 2.010635 times 2.895501. And I get 55.247 for my lower bound. For my upper bound, I'm going to get 69.89. And I guess I'll be 891. So I'm 95% confident that the true mean response for stop, like the true average stopping distance for a car traveling 20 miles per hour, is going to be between these two distances. And again, this is also contingent on what is my sample represent. So we're not really getting into that. So we should only make this generalization to the population from which this sample represents. So this is not necessarily a statement about all vehicles, but it's a statement about vehicles represented by the ones that I did sample. Which in this case, in this data set, I think it's a very old data set with old vehicles. So we would need to do this with newer vehicles if we wanted to apply this result to that population. Prediction interval construction, again, there's a bunch of math that we don't necessarily care about deriving as much as we just like the fact that there is an end result that we can use. So the standard error for y bar plus epsilon now is going to be a little bit more complicated. So it's not just that we're trying to predict the mean response. We're trying to predict the mean response plus whatever that actual difference is going to be, whatever that actual residual is going to be. So we're going to add on a sigma squared into this process for that reason. So all is said and done, we get a very, very similar looking equation with just a slightly updated standard error term over here. So we're not going to actually make a calculation of this as much as we're just going to say it works the same way. We just have a different standard error that we're plugging in a different interpretation. Okay, so I already kind of said the first one, but I'd kind of encourage you right now to pause for a second and think, how do we interpret a 95% confidence interval for mean response? How do you interpret a 95% prediction interval in regression? I have the answers here on the next slide, but I think it's good for you to think about this first. So the generic kind of description here is we're C% confident that the mean response for y at x equals x is between these two bounds. So in the case of the cars, I'll go ahead and say we were 95% confident that the mean stopping distance for cars traveling 20 miles per hour is between those two values. I'm just going to say 55 point and 66 point something. Okay, and again with the kind of the caveat of if we're talking about the population that this sample represents that it came from. If we're making an interpretation from a prediction interval, we just need to be careful. It's a little bit different. So we're basically saying if x equals x, we approximate that c% of all possible values for y should be between these two values, right? So we're making a statement about the distribution of values for y given we're looking at a particular x value. So in the case of a prediction interval for this cars situation, we didn't calculate one, but we'd say something about like if speed equals 20, we approximate that 95% of all possible values for stopping distance should be between whatever values we calculate. And this interval should always be wider. Right, so this is a prediction interval for values of y, as opposed to the other one being a confidence interval for mean response. Oops, and there we go.